We are now entering a new and very important part of Chapter 3, Dynamical Variables and Quantum Mechanical Operators. We start by asking the next major question: how do we represent measurable physical quantities in quantum mechanics? This page is here to show us the roadmap for that discussion. So to make the material easier to follow, this section is divided into 3 subsections. The first subsection is operators, expectation values, and measurement. This may be the most intuitive starting point. We will first discuss what an operator is in general, then what a linear operator is, how expectation values arise in quantum mechanics, and operators corresponding to dynamical variables in classical mechanics. Here the key idea is that the expectation value is a statistical quantity associated with many identically prepared systems in quantum mechanics. So in this first subsection, we are building the conceptual bridge from the familiar idea of measurement to the quantum mechanical formalism of operators and averages. The second subsection is Hilbert space, inner product, and Hermitian operators. This part provides the mathematical framework that makes the operator formalism precise. Once we start writing expectation values and discussing observables, we need a proper mathematical setting. That setting is Hilbert space. Inside that framework, the inner product tells us how to define overlap, norm, orthogonality, and expectation values in a systematic way. Then we introduce adjoint and Hermitian operators, which are especially important because physically measurable quantities must be associated with operators whose eigenvalues are real. So this subsection gives the mathematical structure behind the physics. The third subsection is quantum observables, energy operators, and the Hamiltonian. This is where the formalism becomes directly connected to the physical quantities we care about most. We will discuss how the energy operator appears and why the Hamiltonian plays such a central role in quantum mechanics. In particular, we will see how the Schrödinger equation can be viewed as an operator equation and how the time-independent Schrödinger equation becomes an eigenvalue problem for the Hamiltonian. This is extremely important because later in solid-state physics and semiconductor physics, many of the essential problems reduce to solving Hamiltonian eigenvalue equations. Up to this point, we have discussed the wave function, its physical meaning, normalization, boundary conditions, superposition, and orthogonality. The next major step is to understand how measurable physical quantities are represented in quantum mechanics. In classical mechanics, quantities such as position, momentum, and energy are treated as ordinary variables. In quantum mechanics, however, they are represented by operators acting on the wave function. So before we talk about specific quantum mechanical operators, we first need to understand what an operator is in a more general mathematical sense. So an operator may be understood as a mathematical rule that transforms one function into another function. That is the central idea. We begin with one function, apply a certain operation to it, and obtain another function as the result. Symbolically, if we have a function f of x and an operator a hat x on it, then the result is another function g of x, which is written as shown here. It is read, the operator a hat acting on f of x gives g of x. Here f of x is called the operand. In operator theory, especially in quantum mechanics, the operand is often a function, and in our context, that function will most often be the wave function. In fact, we have been using operators in many mathematical expressions before. For example, d over dx is a differential operator. Partial over partial t is also a differential operator. Del squared is the Laplacian operator, and an integral sign can represent an integral operator. Each of these takes a function as input and produces another function as output. That's what makes them operators. For instance, if I start with a function f of x, then d over dx f of x produces its derivative, which is generally another function of x. Likewise, the Laplacian operator in 3 dimensions acts on a function f is written as shown here, which is the divergence of the gradient of the function f of x. So again, the input is a function and the output is another function. In addition, here we have several illustrative examples, such as multiplying by a constant, cubing a function, differentiating a function, applying an integral type transformation, or forming an expression like the one shown here. These examples are useful because they show that an operator need not be limited to derivatives alone. In general, any well-defined mathematical rule that maps one function into another can be viewed as an operator. Now, in quantum mechanics, not all operators are equally important. The most important ones are linear operators, because the mathematical structure of quantum mechanics is built around linearity. That is why the next page focuses specifically on linear operators. So an operator is a mathematical object that acts on a function and transforms it into another function. In quantum mechanics, the operand is typically the wave function, and as we will see later, measurable physical quantities will eventually be represented by specific operators acting on that wave function. Now let's narrow the discussion to the most important type of operator in quantum mechanics, the linear operators. An operator A hat is said to be linear if it satisfies two conditions. The first condition is additivity, as shown in this expression. The second condition is homogeneity, as shown here, where C is a constant and F and G are functions. These two properties together define linearity. In words, a linear operator distributes over addition and allows constants to be factored out. This may seem like a small mathematical detail, but it is actually fundamental. Almost all operators encountered in ordinary quantum mechanics are linear operators. The reason is that the Schrödinger equation itself is linear, and many of the most important structural results of quantum mechanics depend on that linearity. Now let's look at the examples shown here. Consider the differential operator, d over dx. If we apply it to the sum of two functions, we get the expression shown here. So it satisfies the additivity condition. Also, if we apply it to a constant times a function, we get the expression as shown. So it also satisfies the second condition, homogeneity. Therefore, d over dx, the differential operator, is a linear operator. Now compare that with an operator such as squaring the function. If we define an operation that sends f of x to f of x squared, then for the sum of two functions, we have the expression shown here. Apparently, the squaring operation is not linear. Likewise, the logarithm is not linear because it's not possible to equate both sides of the equation shown here. So logarithm also fails the linearity test. This is a very useful distinction. It tells us that not every operation on a function qualifies as a linear operator. Some do and some do not. In quantum mechanics, this distinction matters because the entire operator formalism is built mainly on linear operators. So at this point, I think it is helpful to keep the following picture in mind. A general operator is any rule that transforms a function into another function. And a linear operator is a special kind of operator that preserves the structure of addition and scalar multiplication. That's why linear operators fit so naturally with superposition, basis expansions, eigenvalue problems, and Hilbert space methods, all of which we will encounter later.